So welcome back, everybody. We have just finished up our discussion of elastic deformation, probably a lot of very familiar topics to you. So we're going to move now into really the second phase of when we look at the mechanical behavior of materials, and that is a little more in the area of what we call plastic deformation. And in this case, the word plastic means permanent deformation. So if we apply enough stress or enough load to a material and start to deform it, the deformation does not go away. And so as we move forward, we'll go back to our quote for the day. This is from Roger Van Ock. He's basically a leadership consultant, but I like the idea of really being able to take new ideas and letting go of what's in the past. So just a little bit of a leadership type quote for you for today. But before we get going, I wanted to hit upon one topic I found in years past when I've taught the class that was not a topic that a lot of students really understood, and that is the difference between what we consider isotropic and anisotropic materials. We saw it in our definition of Poisson's ratio in the last lecture, that isotropic in this case, and where Poisson's ratio was actually applied, is that materials are not impacted by different orientations or directions. I pull material in one orientation, it's going to have the same properties as when I pull it in another orientation if I'm looking at loading it in tension or compression or anything like that. Anisotropic materials, on the other hand, really are not homogeneous in all orientations, so they can change. And we're going to see a lot more of that as we move through the course if we start talking about the properties of materials that you may purchase in your working lives. And that may include rolled plate or different types of long product that you may buy to build large structures. And what we'll see is in different orientations, they actually have slight differences. And so they're slightly anisotropic. It's not a huge difference. It's not the equivalent of what we will see with a carbon fiber composite, where the properties along the orientation of the fibers that are placed in the composite are significantly different than whether they're at a 90-degree normal or transverse orientation to that. So a couple terms to keep in mind and ones that we'll be working with as we move forward. And so in this lecture, and once again, it's chapter 6 of the Callister textbook. I recommend that you read that. And we're going to start a little bit with what plastic deformation is, go into a little bit of tensile properties. So this is where we really start talking about what's going on in the engineering stress strain curves that we typically see, where we'll see where yield strength is defined, we'll see where ultimate tensile strength is defined, and then we'll start getting into some other properties such as ductility and toughness. And ductility really refers to how much you can strain a material, while toughness has a little different definition than what we're used to seeing. Then we'll get into true stress and true strain, an analog to what we consider engineering stress and strain. And we'll get into what the definition there is. And the main difference in the definition between engineering stress and strain is that engineering stress and strain is calculated at the original area or the original length of the component, whereas true stress and true strain change. So we're measuring the instantaneous area or the area as it goes through its stress strain behavior. And then we'll end up really talking about something that's unique to metals, is this ability to strain harden, that as we deform metallic systems, they will actually become stronger. And as we move forward in the course, once we get through our next chapters on crystal structure, we'll start understanding why this is. But we see this strain hardening in our stress strain curves, and what it really shows itself as, or is illustrated as, is a increase in the stress with the level of strain. So as we're deforming a material in the plastic deformation range, it actually becomes stronger. And so the problems that you need to solve, I highly recommend that you do all of them, but the ones with asterisks are part of the assigned problems. And you can go into Canvas and get those problems and complete them and submit them. And so as we move forward a little bit, there's some terminology, and I'm just going to quickly go through this, but ones that you need to maybe study, and these slides are good ones to use. whereas how we define the yield strength, and in this case, we define the yield strength at a certain offset. And we'll get into a little bit of why we do that. Tensile strength is the maximum of the stress strain curve. Ductility is that degree of plastic deformation and the different ways that we can measure it. I'm not going to talk a whole lot about resilience. I like to keep the term there because you will run into it. But it's one that we're not going to cover in any great detail in this lecture. Toughness, on the other hand, is something that we will cover. It will show up on the exam. And it's got some similarities to resilience, but it's something that we can actually pretty much measure just off the stress strain curve. And that's part of the reason why I emphasize it here a little more. And then our definitions and our equations for true stress and true strain. I recommend that you have a good idea, use this slide and these terminologies as a study guide as you move forward. So as we did in the last lecture, what we're going to do is we're going to start with a little video. And this is a unique video. It's a little dated now for you as students. For me, this was, I was still in an undergraduate and graduate school in my early graduate school years when this was done, but the introduction of the Boeing 777 was very much a major technological feat for Boeing in the early to mid 1990s. And this is a test of really plastic deformation in action. And the FAA requires all airlines or aircraft manufacturers before they introduce a new model to pass this test. And this is a wing deflection test. They literally they see how far they can pull the wings off the air before they fail. So literally they're pulling the wings off the aircraft. So it's an interesting video. And as you watch it, take a look at how Boeing is measuring the deflection and the strain and really of what types of plastic deformation, elastic deformation are being shown here.
But the most extreme test of all was still ahead. In the interest of technology, one whole plane would be destroyed. The engineers needed to know if the 777 wings could survive the strongest forces that turbulence or bad handling could produce. They were also interested in whether the same wing design could be used on future, heavier versions of the plane. It would be a simple question to answer, using a plane specially built for the purpose. They would just attach strong cables to the wings and pull upwards until they broke. As the test progressed, the force on the wings became so strong it caused ripples in the fuselage. The engineers hoped that the wing would withstand 150% of the strongest forces it would ever meet in flight. They predicted a wing deflection of about 24 feet before the break.
Retention, we're now holding at 120% design limit load. We'll again make a loads check. It should be a short hold here.
As the tension in the wing increased, the crowd of observers, including many of the people who had lived with the plane for more than 4 years, fell quiet.
Condition 15 in 75 seconds, starting the ramp now. And retention, we're now loading to 130% of design limit load. The ramp rate is again 75 seconds.
Although it was no longer the leader of the team, Alan Mullally was also there to watch. Whichever way you looked at it, the test was a success.
154. 154. 154. 54. The failure mode was, as predicted, compression buckling in the upper panels. We had the failure at about the prediction, the location we predicted on the right wing. On this side, we didn't see the left wing very well, but the observers indicate that the fracture occurred there simultaneously in the same location. But they go it's over.
Yeah, as we see there were a lot of happy engineers there. And as they said, they've been working on this test for 4 years. If they don't pass this test, they have to go back to the drawing board and the aircraft would not be certified by the FAA. So for Boeing, it was a major accomplishment and definitely one that allowed them to put the 777. And I'm sure a lot of you have flown on a 777 aircraft. And so if we look at it, though, there was a lot of plastic deformation. There was a lot of deformation, a lot of mechanical properties of the materials that they used. And it's a test that takes into account a lot of different components because it's more of a system level test than just a material level test. But there's a lot of material components to it.